anomaly scanning detection, obviously you need to build a profile to say normally how much scanning, what's the normal scanning rate, right? So essentially we use this Chebyshev inequality to say that, so here the t is the threshold, and essentially say that what's the probability that you have some observed instance, let's say the scanning rate. That's very different from the mean, right? So it's bounded by this property. So meaning that we only use this to make sure that in a normal operation, the scanning rate is kind of very regular. They don't have big spikes. They tend to be within a very tight range. And if the scanning rate has this property in the normal operations, then it will be very easy to detect any big spike. So we use this to check whether we can apply very simple heuristic. So the result is that we apply it to our network, and so we actually measured for the first phase. If you only use the first phase as the detection module, of course we can catch all the possible worm data, but also it also has a false positive rate, because you do have some inflation-like activity in the network, and then the data reduction rate is actually quite large there, meaning only 10% of data would actually be able to pass that particular check. Okay, so once you pass the first phase, you're only dealing with 10% of the original data, and then the second phase, the false alarm rate by itself actually is also quite high, because there's some hosts that will actually sometimes have some spy and scanning out, for example, some of the P2P kind of traffic, and then but then when you combine, it turns out that we were able to reduce the false alarm rate to be 0 within our experiment. I'm not claiming that that's the general finding, and that's because they don't have overlap, meaning the false positive you have in the first phase, they don't overlap with the second phase. Okay, which is nice. And some results, we actually test this in some large data set, and it turns out that there are not many inflation-like behavior, if some kind of service, like let's say port 80, has inflation-like behavior, then the scanning rate tends to be very, very low, and also the variance is 0, meaning they are if you look at the time window of 1 second, they always stay very tight bound. They don't have like big spikes and all that. So the joy detect traffic, very similar results we've got. But now so you say, okay, you're not convinced because I can easily come up with some scenario to defeat your detection algorithm. All true. Okay, so for example, you say, what about I have some P2P traffic, which can look like worm, because you do have some server that get contacted and then send out to other server, right, to query. So this wouldn't this look like worm? Yes, it will. But using the cascade, you can easily add another module at the top, which will be more sophisticated. For example, you can look at the size of the connection. Let's say P2P connection. I would guess that the payload tends to have a much bigger payload size because you're transferring files and music and everything, right? And also, you can probably do some payload analysis. There will be another sort of more sophisticated kind of analysis. The point is that you want to add the sophisticated analysis modules at the top of the cascade, where you want to filter out a lot of uninteresting traffic. Okay, where you're dealing with very likely intrusive-like traffic. Okay, so if you do this, then you have much better chance. Okay, so that's the argument. All right, so just want to point out that obviously layer kind of architecture is not new, right? So for example, Bro, which is even a signature-based IDS, actually has some notion of doing layering. So essentially, you have network traffic, and then you filter out a bunch of traffic that doesn't concern the network security policy, and then the packet stream will be summarized into what we call event data, which is much higher level semantics, and the size also much smaller. And then you actually apply policy script. So you can see the volume of the stream actually gets reduce at each layer. And the IDS logic actually is in the policy. So I wanted to say that IDS like snort is doomed to fail because it analyzes intrusion at each per packet, and you have such a huge amount of data. So that's why if you have any experience running snort, you have a ton of false positive. Why? Because it's doing intrusion analysis here instead at the higher layer. Okay, so that's so we're working on some theoretical analysis on how they formally analyze different architectures, and then how do you sort of argue one is better than the others. So that would be ongoing work. So another architectural style to reduce false alarm, which is also somewhat obvious, that you can attempt to deploy a lot of sensors in your network. Suppose they look at different segments of a network or looking at different kind of evidence, and then you try to correlate them. And when you correlate, you can actually reduce, you have a chance to reduce false positive. So again, you can think about all these diverse sensors and correlation as kind of layer architecture, meaning that the sensor already filtered out data that's not interesting. The sensor only sends reports to the correlation engine, right? So the report you can think about as very much a interesting event data that would likely to actually would likely be related to the real intrusion, right? So then of course then the research question then what event do you monitor? But that's what the IDS people are worrying, and then the correlation engine will actually analyze the event data from the sensors and then make a sense of whether there's actually intrusion or not. So the argument is that the event data would already have very high base rate, and the question we want to answer is that how many sensors? For example, there are many questions here, right? But one particular question that we were looking into is that how many sensors observation are sufficient for you to actually have very confident output to say this is a intrusion, right? So the example of such sort of a sensor and then correlation, so kind of two-layer system is the Honeystat system that we built. Essentially, that's another. So we were working on worms last year like everybody else. So that's why I use those examples. I don't necessarily say these, the worm research is great, but just I think it's very intuitive. Everybody understands worms, and so anyway, so we work on Honeystat, and the idea is that the general idea is that we can use some VMware, right, to do honeypots, and then essentially the one thing about worm is that it would normally blindly scan a lot of hosts. So if you have a whole farm of honeypots, then it's likely that you will see you will see the same strange behavior across more than one honeypot. Okay, so that's the idea. So you deploy a bunch of honeypots. I mean, I think hardware actually is very cheap. What's expensive is the IPs. How do we get a large segment of IPs from your IT group here? And we were lucky to get that. So then the research question here is how do you correlate the alarms from the honeypots so that this is a worm versus somebody just scanning or somebody just randomly poke at your honey net. Okay, so that's the intuition, and that's system details. So essentially we have two phases again. So one phase is the black box, meaning each honeypot would actually try to filter out some incoming traffic and report interesting activity. For example, they will say, okay, my honeypot is sending outgoing traffic. Now that's very strange activity. So whenever you have honeypot sending outgoing traffic, this is something that you want to look into. Okay. And then, so essentially, the correlation phase would actually attempt to explain for each honeypot what triggers the outgoing traffic. Suppose for honeypot A, you say, okay, the outgoing traffic is triggered by the incoming traffic to this particular port. You say, okay, that's a interesting pattern.